Problems involving heat engines are fundamentally problems in the first law of thermodynamics. A heat engine is any device that converts heat partially to work. How do we determine the thermal efficiency of a heat engine? Find out, stick around, watch and learn. The question is, in one cycle, a Carnot engine takes in 8.00 times 10 to the fourth power joules of heat and thus 1.68 times 10 to the fourth power joules of work. The temperature of the engine's cold reservoir is 25.0 degrees Celsius. Question letter A. What is the efficiency of this engine? Question letter B. How much heat does this engine exhaust per cycle? And question letter C. What is the temperature in degrees Celsius of the hot reservoir? As shown in this schematic energy flow diagram for a heat engine, we say that a heat engine takes in energy in the form of heat, all right, from a hot reservoir, and this amount of heat that is used is labeled as Q's of H, and this energy is at a temperature labeled here as T's of H. All right, so the engine uses some of that energy to do work, W. And then the rest, or the remaining energy that is not converted into useful work, will simply be rejected or expelled as or in the form of heat into what we call the cold reservoir. All right, and this expelled amount of heat is denoted by capital Q sub C. And the temperature at this cold reservoir is denoted by Tc or capital Tc. Both Th and Tc, um, when doing problems, especially when determining the efficiency of the heat engine, have to be expressed in Kelvin or absolute temperature. Now, the fraction of the heat from the hot reservoir that is converted into work is called the thermal efficiency of the engine. All right, so for question letter A, uh, we are going to calculate this thermal efficiency. All right, but before that, we first take a look at the given data in this problem. So we have the temperature at the cold reservoir equal to 25.0 degrees Celsius, which when converted to Kelvin is equal to 298 Kelvin. We are also given the input heat labeled as Q sub H, and that is equal to 8.00 raised to the fourth power joules. And the work W, all right, the work W is given as 1.68 raised to the fourth power joules. So, the first question, letter A, is asking for the thermal efficiency of the heat engine. And this can be calculated using the formula efficiency is equal to the work done, W, divided by the input or heat input, Q of H. And that is, when we substitute, we have for the work done 1.68 raised to the fourth power joule to be divided by the amount of heat input 8.00 times 10 to the fourth power joules. All right? So, simplifying, we will get the value for the efficiency equal to 0.21, which can also be expressed in terms of percent. That is, the efficiency or thermal efficiency E is just equal to 21%. And this efficiency means that only 21% of the heat input from the hot reservoir is converted to useful work or mechanical energy, right? So the rest of the input energy is expelled into the cold reservoir. Moving on now to question letter B. Question letter B is asking for the amount of energy that is wasted or expelled into the cold reservoir. So that's our target variable, denoted here by capital Q sub C. This is computed simply by subtracting the useful work done from the heat input. Okay, in the diagram, we have that equation. All right. The W or the work W is equal to Q sub H plus Q sub C. All right. But since we're looking for Q sub C, the equation for that will be the work done W minus the heat input Q sub H. All right. Substituting, the work done is 1.68 raised to the fourth power joule minus the input heat or heat input amounting to 8.00 raised to the fourth power joules. All right. So subtracting these two quantities, we will get the value for QC equal to negative 6.32 raised to the fourth power joule. And what does this mean? All right, this means that 6.32 raised to the fourth power joules of heat leaves the engine during each cycle. All right, and actually, this amount of heat that is expelled to the cold reservoir, all right, is a wasted heat. It can no longer be used, all right? So it just uh, goes into the surrounding. All right? And finally, for question letter C, we are asked to find the temperature of the hot reservoir, denoted by capital T sub H. All right? Uh, from the Carnot efficiency formula, all right, the efficiency of a Carnot engine is expressed as 1 minus Tc over Th, all right? And since we are looking for Th, we just derive the formula, isolate Th, and we will be able to get the working formula for Th, which is equal to Tc divided by 1 minus the efficiency. All right? Substituting, we have 298 Kelvin as the value of the temperature in the cold reservoir. Then divided by the difference of 1 and the efficiency 0.21. Doing our math, we will get the value for the TH that is equal to 377 Kelvin. But since in the problem, the temperature in the cold reservoir is originally expressed in degrees Celsius, the temperature in the hot reservoir, or our computed value for TH, when converted to degrees Celsius, that is equal to 104 degrees Celsius. So that is uh, the temperature at the hot reservoir. So that completes our solution and answers to this problem. Till our next episode, inshallah. Thank you very much for watching. Please follow me in my FB page, and please don't forget to subscribe to my YouTube channel.